Space is often described as beautiful, and from a distance it truly is. Points of light, slow spirals of galaxies, nebulae stretched thin across the dark. From far away, it looks composed, almost deliberate. But beauty is not a promise of safety. Sometimes it's only a surface property. If you keep looking, not scanning, not searching, just letting your attention settle, something else begins to show. Between stars, there is no backdrop. Between galaxies, there isn't even that. There is no pause. There is, almost, everything missing. Vast regions where nothing happens, not dramatically, just continuously. No light, no motion that matters, and eventually, not even a clear sense of where. The universe isn't empty in the way a room is empty, it's diluted past intuition. And that may be what makes it unsettling. We tend to imagine fear in space as something active. Explosions, collisions, stars tearing themselves apart. But far more often, the universe is disturbing because nothing responds. Light fades without resistance. Time stretches without comment. Direction stops being useful. There are regions where a planet could be erased in less than a second. Others where entire galaxies drift, not colliding, not escaping, just moving, without a clear reason we can point to. And there are boundaries beyond which information simply does not return. This isn't science fiction. It isn't metaphor. These places exist in the same universe as your body, your thoughts, this moment. Before we go further, a brief pause. If you enjoy slow, careful explorations like this, liking the video or subscribing helps the channel continue. It's what makes long, quiet formats possible. This won't be a countdown. Fear doesn't organize itself that neatly. Instead, we'll move through regions where you could travel for hundreds of millions of years without seeing a single star. We'll look at places where reality behaves slightly incorrectly and where the universe's own past feels incomplete. We'll talk about forces that move entire galaxies, even when we can't fully see what's doing the moving. And about horizons where light stops being informative. The most unsettling places in the universe don't necessarily destroy you. They do something quieter. They remind us that reality is not obligated to be understandable, or full, or arranged around an observer. So we'll begin there. Not with violence, not with catastrophe, but with near total absence. Part 1. The BOÖTES Void. On maps of the universe, most regions are marked by light, clusters, filaments, dense intersections where galaxies collect. Structure leaves traces. And then there are places where the map almost falls silent. One of those regions lies roughly 700 million light-years away, in the direction of the constellation BOÖTES. There is no visual warning, no dark patch visible to the eye. Nothing about that area of sky suggests what's missing. The disturbance only appeared once astronomers began mapping where galaxies should be. According to every large-scale model, that region ought to have been crowded. It wasn't. The BOÖTES void spans about 330 million light-years. Inside that volume, there are only a handful of galaxies where tens of thousands were expected. Not dim ones, not hidden ones. They're simply not there. To grasp how extreme this is, it helps to stop thinking locally. Imagine the universe as an ocean scattered with islands of light, galaxies as continents, clusters as archipelagos that hint at underlying structure. The BOÖTES void would be a cavity in that ocean, large enough to swallow superclusters without noticeably changing its emptiness. This isn't a gap between structures. It isn't a quiet neighborhood. It's a region where matter itself largely failed to arrive. Astronomers didn't set out to find it. They encountered it in the early 1980s while doing something much more ordinary, counting galaxies. Where the models predicted density, the surveys returned absence, a hollow vast enough to force a rethink of how evenly the universe is built. We now know the cosmos resembles a web. Long filaments of galaxies stretch across space, woven by dark matter, separated by enormous voids. But even among those voids, BOÖTES is an outlier. Near its center, you could travel for hundreds of millions of years in any direction without encountering another galaxy. No spirals hanging faintly at the edge of vision, no diffuse glow, nothing to suggest scale. The nearest visible light would take longer to reach you than our species has existed. If you were drifting there, you wouldn't feel motion. There would be no reference points, no horizon that meant anything, no background against which to judge distance. Even the cosmic microwave background, the faint afterglow of the Big Bang, would appear slightly dimmer, thinned by the lack of surrounding matter. In that environment, the universe would feel less like a place and more like a condition. Distance extended past usefulness. How something like this forms is still an open question. Most models suggest it's a natural result of gravity pulling matter into dense filaments as space expanded, leaving vast regions behind. Others argue the BOÖTES void may not be a single structure at all, but many smaller voids overlapping, emptiness compounded. And then there are ideas that stretch further. A few physicists have wondered whether regions like this could be imprints, not of internal evolution, but of interaction, a neighboring universe brushing against ours in the earliest moments. There is no evidence for this, and most researchers remain skeptical. But the fact that such questions surface at all says something about the scale of the anomaly. What makes the BOÖTES void unsettling is not just its size, it's what it quietly implies. That most of the universe is not made of stars or galaxies or anything that glows. For every bright cluster we point to, there are enormous volumes in between where almost nothing happens. If you could stand at the center of the BOÖTES void and look around, you wouldn't see a single star, just darkness. And maybe, after waiting longer than feels reasonable, a faint flicker at the edge of perception, a distant galaxy barely there. One point of light surrounded by almost everything else. The BOÖTES void isn't just a hole in space, it's a glimpse of what the universe mostly consists of. Not matter, not structure, but the long, quiet stretches in between. Part 2. The ERIDANUS supervoid. The BOÖTES void shows how empty the universe can be. But there is another region where emptiness does something different. It leaves a trace. High above the plane of the Milky Way, in the direction of the constellation ERIDANUS, astronomers were studying something much older than galaxies. Not stars, not clusters, the background itself. Every direction we look, the universe glows faintly. The cosmic microwave background, radiation released when the universe was young, dense, and still hot enough for matter and light to remain tightly coupled. It's the oldest light we can see, a nearly uniform signal spread thin by expansion. But in the early 2000s, data from the WMAP satellite, later confirmed by Planck, revealed something unexpected. One region of the sky was noticeably colder than the rest. Not cold in the everyday sense, but measurably colder than the surrounding universe, a deviation large enough to feel uncomfortable. This became known as the cold spot. At first, it was tempting to dismiss it. Random variation, statistical noise. The cosmic background isn't perfectly smooth. Small fluctuations are expected. But this one lingered. It was too large, too coherent, and eventually something else aligned with it. In the same direction, astronomers identified a vast, underdense region of space, nearly 1 billion light-years across, containing far fewer galaxies than predicted. This was the ERIDANUS supervoid, a structure so large that it pushes against the limits of standard cosmological models. Not simply empty, excessively so. To see why this matters, it helps to think about how ancient light travels. Photons from the Big Bang cross billions of light-years, passing through regions of gravity and void. They gain energy falling into gravitational wells and lose energy climbing back out. Usually, these effects balance, but across something as large and empty as the ERIDANUS supervoid, they don't. Photons lose slightly more energy than they regain. When they emerge, they carry less heat. They arrive colder. The larger and deeper the void, the stronger this effect becomes. It's subtle, but measurable, as if the universe exhales there and never quite recovers what it released. If you were drifting through the ERIDANUS supervoid, there would be no dramatic boundary. Galaxies would thin gradually, then almost vanish. The sky wouldn't darken suddenly. It would just stop offering reference points. You wouldn't feel cold, but the universe would. A quiet deficit of energy, a place where even the oldest light arrives diminished. What unsettles researchers is not just that this void exists, it's the possibility that it shouldn't. Some have suggested the cold spot may not be a product of internal evolution at all. In certain models, our universe is one bubble among many. In its earliest moments, those bubbles may have interacted. If that happened, the ERIDANUS supervoid could be the residue, a region where our universe remembers contact with something outside its own history. There is no direct evidence for this, and many scientists argue the cold spot remains statistically plausible. But the numbers don't rest easily. The feature is large, isolated, and difficult to dismiss. Whether coincidence or imprint, the ERIDANUS supervoid remains one of the strangest structures we know. A place where emptiness reaches backward in time and alters the oldest light in existence. Not a void in space alone, a void in how the universe recalls its beginning. Part 3. The Great Attractor. On the largest scales, the universe is not static. Space expands, galaxies drift, clusters deform under gravity. None of that was surprising. What surprised astronomers was the direction. When the motion of nearby galaxies was measured carefully, a pattern appeared. Not randomness, not even expansion alone. Everything seemed to be moving the same way, our Milky Way included. Along with billions of stars and planets, we are traveling through space at over 600 kilometers per second, not away from a single point, toward a region, roughly 200 million light-years away in the direction of Norma and Centaurus. Whatever lies there exerts a gravitational influence strong enough to distort the motion of entire galaxy clusters. Astronomers gave this influence a name that reflects the uncertainty: the Great Attractor. Despite how it sounds, the Great Attractor is not an object. It's not a black hole, not a star, not even a single cluster. It's a region of excess mass, spread out, partially hidden, and difficult to map. Our local group of galaxies is caught in this flow, not falling violently, but drifting like debris carried by a slow, deep current. The problem is visibility. The Great Attractor lies behind the dense disk of the Milky Way. Gas, dust, and starlight block our view in most wavelengths. Astronomers call this area the zone of avoidance. It's a reminder that even within our own galaxy, there are places we struggle to see through. Using X-ray and radio observations, scientists have identified part of what lies beyond. A massive concentration of galaxies known as the Norma cluster, rich in dark matter, filled with superheated gas. But the pull we experience extends beyond this structure. The gravitational influence is broader, deeper. The Great Attractor appears to be only one feature within a much larger system, the Laniakea supercluster, a vast region containing tens of thousands of galaxies, all moving along coherent flows towards shared gravitational basins. In this picture, galaxies are not isolated. They are participants, their paths shaped by mass distributions we cannot fully observe. And beyond Laniakea, the motion may continue. The Shapley concentration, one of the most massive structures nearby, may be exerting its own pull, drawing entire superclusters toward it. At that scale, it becomes difficult to define where the current begins, or whether it has an end at all. What makes the Great Attractor unsettling is not its mass, it's the realization that we are already moving, not toward a visible destination, but along a gradient we did not choose. This motion is not dramatic. There is no sensation of speed. It is steady, persistent. Billions of years from now, the Milky Way will merge with its neighbors, drawn deeper into Laniakea's structure. Beyond that, expansion will isolate what remains, pushing distant galaxies past our horizon. The Great Attractor itself will remain obscured, unreachable, unresolved, a direction without a clear endpoint. It is gravity without a face, and a reminder that some of the most influential forces in the universe are the ones already shaping our path, quietly, whether we notice them or not. Part 4. Magnetars. Some of the most extreme objects in the universe appear only after something else ends. When a massive star exhausts its fuel, its core collapses. The outer layers are blown outward in a supernova, and for a brief time, the explosion outshines an entire galaxy. What remains is usually quiet, a dense remnant, cooling, largely inert. But occasionally, the collapse leaves behind something unstable. If the core is too light to form a black hole, it becomes a neutron star, about 20 kilometers across, more massive than the Sun. Matter compressed to the point where atomic structure no longer behaves normally. A teaspoon of it would outweigh a mountain range. Most neutron stars are strange but predictable. A small fraction are not. Some are born rotating extremely fast, their magnetic fields amplified during collapse to levels that strain our understanding of matter itself. These are magnetars. A magnetar's magnetic field is the strongest known in the universe, trillions of times stronger than Earth's. Strong enough to distort electron orbitals, to alter the behavior of atoms far beyond the star's surface. If you approached one, not close, just closer than comfortable, its magnetic field would scramble electronics and tear molecular bonds apart long before gravity mattered. But magnetars are not stable objects. Their magnetic fields are twisted and stressed, locked into configurations that cannot last. And when that stress releases, the star fractures. These events are called starquakes. They are not gentle. In less than a second, a magnetar can release more energy than the Sun emits over hundreds of thousands of years. The release comes as an intense burst of gamma radiation, so bright that, for a moment, it dominates the high-energy sky of the entire galaxy. In 2004, a magnetar known as SGR 1806-20 produced a flare so powerful it briefly altered Earth's upper atmosphere. It was 50,000 light-years away. Had it been significantly closer, the consequences here would have been severe. Not extinction level, but enough to damage the ozone layer and expose the surface to increased radiation, all from an object smaller than a city. Magnetars do not persist. Over tens of thousands of years, a short span cosmically, their magnetic fields decay. The star quiets. What remains is a more ordinary neutron star, still dense, still exotic, just no longer volatile. That brevity is part of what makes magnetars unsettling. They don't dominate the universe, they flicker within it. Small, short-lived, and disproportionately powerful. Magnetars don't reshape galaxies, but they remind us that extreme physics does not require scale. Sometimes danger is compact, localized, and already over by the time we understand it. Part 5. Quasars. At the center of nearly every large galaxy, there is a black hole. Most of them are quiet. They sit embedded in stellar orbits, feeding sporadically, leaving only subtle gravitational signatures. But some black holes are not quiet. They are active. When large amounts of matter fall toward a supermassive black hole, the process does not end at the event horizon. Gas spirals inward, forming an accretion disk. Friction and magnetic forces heat this material to millions of degrees. The energy has to go somewhere. It leaves as radiation. Across the electromagnetic spectrum, from visible light to X-rays and gamma rays, the region around the black hole becomes luminous, overwhelmingly so. This is a quasar. A single quasar can outshine its entire host galaxy. Not because it is large, but because the conversion of mass into energy near a black hole is extraordinarily efficient. Along the black hole's rotational axis, something else happens. Jets of charged particles are launched outward at nearly the speed of light. These jets can extend for millions of light-years, cutting through intergalactic space. If one were aimed directly at Earth, the effects would be immediate. The atmosphere would be stripped. Surface life would not survive. There would be no warning in any human sense. Just an absence afterward. Quasars were far more common in the early universe. Galaxies were closer together. Collisions were frequent. Black holes had access to abundant fuel. During that period, quasar light shaped the evolution of galaxies. It heated surrounding gas, regulated star formation, and carved structure into the cosmic environment. One of the most extreme examples we know is TUN 618. At its center is a black hole with a mass exceeding 60 billion suns. Its luminosity once surpassed the combined light of the Milky Way. Objects like this did more than illuminate the young universe. They altered it. Over time, their fuel diminished. Accretion disks thinned. Jets weakened. The quasar phase ended. What remains today is a dormant black hole, quietly anchoring a galaxy's core. When we observe quasars now, we are not seeing the present. We are seeing echoes. Light that has traveled for billions of years through an expanding universe to reach us. Each quasar is a reminder that brightness and violence are sometimes the same phenomenon, that the most radiant structures can also be the most destructive, and that the universe, especially early on, was not a gentle place. Part 6. The Event Horizon. Every black hole has a boundary. Not a surface you could touch, not a physical shell. A limit written into space-time itself. This boundary is called the event horizon. From far away, a black hole behaves like any other massive object. It bends space, objects orbit, nothing seems especially strange. That impression doesn't last. As you approach the event horizon, time begins to behave differently. Not symbolically, not as a figure of speech. According to general relativity, time genuinely slows. To a distant observer, anything falling toward a black hole appears to decelerate. It never quite crosses the horizon. It fades, redshifts, becomes unobservable. From the perspective of the falling object, none of that is visible. There is no surface, no sudden force. The horizon has no texture. You cross it without noticing anything at all. And that is where the discomfort lies. Because once that boundary is crossed, the future contains no version of escape. Not because of acceleration or force or pressure, because of geometry. Inside the horizon, space-time tilts so completely inward that all possible paths forward lead deeper toward the center. Out stops being a direction that time allows. Inside, space and time trade roles. Moving forward in time means moving inward. Pausing is meaningless. Turning around is not an option. Even light cannot find a trajectory outward. Not because it slows, but because no outward paths exist. The event horizon is not where destruction occurs. It is where alternatives vanish. From the outside, however, black holes are almost boring. They can be described by just a few numbers: mass, spin, charge. Everything else disappears from view. And that leads to a problem. If something carries information and falls into a black hole, where does that information go? Part 7. Is information really lost? Physics is built on an assumption that information is never destroyed. Systems evolve, energy spreads, structures collapse. But the complete description of a system should always be recoverable, at least in principle. Black holes challenge that. Imagine throwing a book into one. Every page, every letter, every microscopic configuration. From the outside, nothing remains. The black hole grows slightly more massive, its surface area increases, but the details vanish. If the black hole later evaporates, as Stephen Hawking showed it must, the radiation that emerges appears thermal, random, featureless, no trace of the original structure. If that's correct, information is destroyed, and that breaks physics. Cause and effect lose precision. The future can no longer encode the past. Quantum mechanics does not allow this. General relativity seems to. Both theories work extraordinarily well, except here. At the edge of a black hole, they contradict each other. One proposal is that information is not lost, but redistributed, encoded on the event horizon itself as microscopic patterns. This idea led to the holographic principle, the suggestion that everything inside a volume of space may be described by information on its boundary. A radical idea, but a serious one. Another possibility is less satisfying. Information escapes in Hawking radiation, but only as subtle correlations. Recoverable in theory, but only after waiting longer than the age of the universe. The laws are preserved. Practical meaning is not. There are also more extreme ideas: firewalls, fuzzballs, revisions to space-time itself. Some models suggest the event horizon is not smooth, that crossing it would be violent. If so, something fundamental must be abandoned. Either space-time continuity or the principle that information is preserved. What gives this paradox weight is not the mathematics, it's the implication that space and time may not be locally real, that reality may not store its history the way we assume. Black holes are not just objects, they are stress points, places where the universe is forced to reveal inconsistencies in our descriptions. So far, it hasn't resolved them. We have equations, arguments, decades of debate, but no consensus. Only a quiet tension at the center of modern physics. A reminder that even now, some questions fall inward and do not return. Part 8. Could the universe end without a bang? When people imagine the end of the universe, they tend to picture drama, a collapse, a final explosion. But the universe does not require a cinematic ending. Some of the most plausible futures are quiet. Observations show that the universe is expanding. More than that, the expansion is accelerating. Distant galaxies are not just receding, they are being pushed apart faster over time. We call the cause dark energy because we do not understand it. We understand its effect. If this acceleration continues, the future grows increasingly empty. Galaxies pass beyond one another's horizons. Light emitted too late never arrives. Over time, the observable universe shrinks, not because space collapses, but because it stretches too quickly to keep regions connected. This picture is known as heat death. Stars exhaust their fuel, black holes evaporate, temperature differences flatten out. Eventually, nothing meaningful happens anymore. Time continues, but without markers. There are alternatives. If dark energy increases, the universe could end in a big rip. Structures are torn apart, not all at once, but in sequence. First clusters, then galaxies, then atoms. Even this would not feel sudden. It would unfold according to the universe's expansion history. And then there is a quieter idea, that the universe could decay, a quantum transition in the vacuum itself. No signal traveling ahead of it, no warning. The laws of physics would reorganize, and a new phase of reality would expand outward at nearly the speed of light. If that happens, we would never observe it. All of these endings have something in common. They are not conclusions. There is no final moment, no universal witness, just a gradual loss of structure, of complexity, of distinction. The universe does not end, it thins. And perhaps that is the hardest outcome to accept. Not destruction, but dilution. After all of this, after collapsing stars, regions of absence, forces we cannot see, and futures that fade instead of ending, one question remains. Not about the universe, about the fact that it can be noticed. The universe does not require observers. Galaxies would still collide, black holes would still form, space would still expand according to equations that do not ask whether they are understood. And yet, here we are, made of the same particles as stars, arranged into a structure that can reflect on its own existence. For a brief interval, the universe becomes aware of itself. This is not a metaphor. Every thought you have ever had is a physical process. The same constants that allow atoms to hold together allow neurons to fire. The same expansion that pulls galaxies apart creates a long, quiet window in which complexity can persist. Not indefinitely, but long enough. We often ask whether the universe is hostile, whether it is fine-tuned, or whether it is indifferent. Those may be the wrong questions. The universe does not optimize for permanence. It does not guarantee comfort. It does not ensure understanding. It permits structure, and then it moves on. Stars burn out. Civilizations, if they arise, encounter limits they cannot engineer away. Energy spreads, options narrow. Even space-time may give way to something deeper and unfamiliar. Nothing here is promised to last. And yet, meaning appears. Not because the universe provides it, but because observers do. Meaning appears when something that won't last still takes the time to notice itself. When a finite mind faces an unbounded backdrop and chooses attention instead of avoidance. Perhaps that is the quiet anomaly. Not that the universe exists, but that, briefly, it can be contemplated. Imperfectly, partially, enough to feel both small and connected. Before we end, thank you for staying with this journey. If the video slowed your thinking, if it allowed an idea to linger instead of resolving cleanly, then it has done what it was meant to do. I'd be curious to hear what you think defines the true edge of the universe. Distance? Energy? Or our ability to make sense of it at all? And if you want to keep walking these quiet paths where physics meets uncertainty, consider subscribing. The universe is not designed for us, but it does allow us to ask. See you next time.